Okay, good morning, everybody. So we're going to devote today's class time lecture to going over questions that people have. So I'm sure a lot of you have questions, old problems that you want me to go over. We can do old problems. Yes, we can. You have specific ones in mind? Daniel, did you have something specific in mind there? Can't find it. Okay, can we go over 2008 full section B? Which one? Is this exam 1, 2, or final? UDAVA. Exam 1. This one here. Tell me with the recurrence equation. Are you talking about the recurrence equation? The one on the screen? Yes? Okay. So why don't we do that? All right. So you will definitely have a question like this, not exactly, but like this one here. All right. Let me see if I can grab that. I don't know if it'll let me grab it. I can just tape it again if I need to. Okay, so let's go out of here. And Okay, so here we have some solutions. So again, this is full 2008, exam 1, section 2, part 2, problem 2. Okay, so part 1, all right, we'll just start with that. So I don't need an exact algorithm here, but here's what I want you to notice, okay? Right? You have 8 subproblems, right? Each subproblem is half the size. Okay, so how do we do that? So let's say we get an array, call it A. All right, so n equals len of A. Again, you don't really need this kind of code here. Probably be easier if we switch to Courier. All right, so what do we do? So how do we get a subproblem that's half the size? Right, so we can create, it doesn't even matter what the subproblem is, right? So we could say B equals A from 0 to n divided by 2. Probably a good idea to do an int there. Okay, so now we have a problem that's half the size. And how do we get 8 subproblems? We call algorithm, or we could do it like this.
For loop?
We could do it, we can do it in a for loop. So we could say for I in range 8, right? You could say call the algorithm on B. Okay, now there's another part here, right? Part of it was to do n units of work, right, on top of that. So we can do it before, during, or after. So let's just do it over here. So we could say for I in range n, I don't know, we could do some work, right? So some arbitrary then over here, oh wait, we're supposed to be half the size or a quarter of the size? What did it say in the exam? What did it say in the exam? Is it n over 2 or n over 4? N over 4, so we need to make this a quarter of the size, right?
Professor,
Yeah.
where do we put the base case?
Okay, you want to have a base case. That's not a bad idea. So what are we supposed to do in the base? What did it say in the base case?
It's T of 1 equals 1.
If n equals 1, we want one operation, right? Yeah.
Yeah.
Okay, so there are obviously a lot of ways to do this, but We don't even need to return there. We could just say, okay, we need to put, and then get rid of the return here. We could say else. Wait. Okay, any questions on that? All right, so the question, I guess what the student was really asking is about the recurrence itself. Okay, so I'm going to get out of the Courier new. And you know what? Do this, but let me get another old solution and use this as a template, okay? Because again, all these problems, at least the ones I'm going to ask you, are going to be similar to what we have done before. Just going to copy all this. Okay. Okay, so I'm not looking at the problem. Can someone tell me what the problem was? It's T of 1 equals 1, and T of n equals T of n equals T of n divided by 4. And there's an 8 here. Okay, plus n?
Yes.
Okay. All right, so let's do this. So what is our A?
Eight.
A is 8. And what is our B?
4,
4. And what is our C?
1.
1. So our log 4 of 8. Okay, what's log 4 of 8?
1.5.
It's 1.5. Okay, and that's greater than 1. So therefore, it's going to be dominated by that. Okay, maybe I can make this a little bigger. So let's make this whole thing. Okay. All right, so, okay, let's go to the, try to do this. Okay, so what is our assumption going to be here? Again, I took a solution for another exam, and we're just going to modify it as needed. So this is going to be 4 to the k, and this is going to be a 4. Then I use a domain transformation, right? So this is going to be 8. This is going to be 4, and this is going to be 8 again, and this is going to be 4 to the k. And our initial condition was what, 1? Initial condition is 1? Yeah?
Yes.
Okay. And I put a 4 there, and a 4 there, 4 there, and a 4 there, and that's good there. Now I do a range transformation. So I'm going to divide by what over here?
8 to the k.
Correct, 8 to the k, and that's going to be equal to 1 over 8 to the k times 8 of k minus 1. This was 4 to the k, and so what am I going to get here? I'm going to distribute it out. I have an 8 here and an 8 there, and this is a 4 there, and this is an 8 there, and let's move it to the next line. Okay, so I get 4 to the k. That's equal to s of k over 8 to the k minus 1 plus 1/2. And that gives me r of k minus 1 plus right? And over here, what do I get? What do I change it to over there? Just make this more in the middle. It's going to be 8 to the 0. S of 0 is what? 1, right? Okay, so I write out all the equations. And what do I have on the right-hand side?
Half.
Correct. And I do the same for all of them. And now I add up the equations and I get 1/2 for j to 1 to k. And r of 0 is what? 1 is equal to 1/2 for j to k. And I move the 1 to this side. That's good. And now the 1 gets moved into the summation. Everyone see that? This is important, right? So you're moving that 1, the loose 1 over here, into the summation. Now it goes from j equals 0 to k. Now we use our formula for the geometric series. So we don't have this 1 anymore. Let's get rid of those 1s. That's going to be confusing. All right, so let's plug in. So this is 1/2, the k plus 1 minus 1. And we have 1/2 on the bottom because that's our ratio. And again, we have 1/2 over here. Why do we have that twice? I guess we don't need it twice. Okay, and we flip the signs. So we flip it around. And here we have 1/2 on the bottom. We cross multiply, we get 2 on the top. And 1 minus 1/2 to the k plus 1 there. And we get 2 minus, one of the 2's cancels, and we get 1/2 to the k, right? Is that going to be 1/2 to the k? It's important we get this right, otherwise we get messed up later. So if I take 2 over 1/2 to the k plus 1, I will get 1/2. Okay, so now I'm going to substitute back. So what do I put over here? Where my cursor is? Give you hints. What is r to the k? It's s of k over 8 to the k. When I substitute back, I need to multiply by 8 to the k. I multiply by 8 to the k. And what did I have here? I had 2 minus 1/2 to the k. So I get 2 times 8 to the k minus, what am I going to get over here?
4 to the k.
4 to the k. Good. Now I just use to substitute back, and this is going to be 4. And so it's going to be 2 times 4, not 4, 8 to the log base 4n minus 4 to the log base 4 of n. So that gives me 2 times n to the log base 4 of 8. And over here, we get n to the log of 4 of 4, which is just 1. Okay, and we can simplify that one step further. So that's equal to n squared minus n. Okay, so now we're going to test it. Okay, so according to the original recurrence, what did we have? We had an 8 there and a 4 here. And we had, what was it to test? T of 4? What are we testing? T of 4?
Yes.
T of 4. Okay, so we get 8 and 4 over 4 plus 4 equals to 8 times T of 1 plus 4. So T of 4 is equal to 8 times 1 plus 4 equals 12. Okay, now let's compare that to the formula. According to the formula we got, formula says it's 2 times n squared minus n. That's 2 times 4 squared minus 4. And that's 2 times 16 is 32. Minus 4 is 28. So we made a mistake. We made a mistake. Okay, so we go back to the drawing board. Where the key down says log 4/8. Oh, thank you. Wait, over here, right? Yes, thank you. So this is 1.5. Okay, so therefore, this is 1.5. And this is 1.5. So what do we get now? Okay, so 4 to the 1.5 is,
8.
yeah, let's write it out so everyone understands how to do that, because that's not fractional. So that's the same as 4 to the 3 to the half. Okay, minus 4. So now we get, let's just write this out. And that's equal to 16 minus 4, and 16 minus 4. Okay. Good. Daniel, is that the one you wanted? Daniel? Okay. All right. Here, I just posted. Okay, it was question 5 in summer 2019 exam 2. Okay. So what is it? Summer 2019 exam 2. This hyperlink? No. What do you say, page 58? Is this it? These are, oh, okay. Okay, this one here? Is this it? Yes? Okay. All right, this looks like a nice problem here. Okay, you may assume any standard representation of a graph and also make use of other standard algorithms in solution to the stated problem. Okay, so how do we determine if an undirected graph is a tree? So you can run DFS on it. And again, if you want to do, you run a DFS and you keep track of how many vertices you hit. Okay, if you get, well, if you hit all the vertices and only did v minus 1 edges, right? So if you hit a vertex a second time, what does that mean? What happens if you hit a vertex that you visited already? You have a circuit, right? So that's no good, right? So basically the trick is you're running a DFS on your graph, use an adjacency list, because otherwise it will take, I'm sorry, an adjacency list or adjacency table. And if you hit a vertex, you try to visit a vertex as a neighbor from something that has been visited already. So that's going to be a problem. That means you have a cycle there, right? Okay, determine O of V time if an undirected graph contains a cycle. So that's going to be basically you're doing the same thing. The previous one, you're counting the number of edges that you traverse. Okay. Question, what we'll be using in the exam to represent no path? I didn't catch. Oh, okay, I understand what you're saying. You don't mean no path, you mean no edge. But yes, that's a valid question. So I don't think it really comes up, but if it did, I would either tell you or you would have discretion. So if I give you a code snippet, I guess I would have to tell you what assumption we're using. It's likely to, be a code snippet that we've seen. So many cases we use 0 at the end of the day, but I would have to tell you that. Okay, it's a fair question. Same for transitive closure. So transitive closure, we're going to use. Yeah. So I understand the question. If it's relevant, I will specify. Okay. I just have to save the recording from the previous class. Give me 1 second here. All right, it's just getting stuck. Okay, determine in O of V plus E time if a directed graph contains a cycle. All right, so the question is, why is this different than B? In B, O of V, and in this question, it's O of V plus E. So if it's an undirected graph, how do I know if there's a cycle? Once I hit more than V edges, I know there's a cycle because it's undirected. Okay, in a directed graph, that's not necessarily true because the direction on the edges. So in this case, I would need to look for a back edge. Everyone remember what a back edge is? A back edge is an edge from a vertex, from a descendant to an ancestor. And one way to do that is using the begin and finish times, right? So if we go back to a vertex that we began and did not yet finish, right? If we hit a vertex that we began and we did not yet finish, and we hit it again, that's going from a descendant back to the ancestor. Okay, question D. How do we get the transitive closure of a directed graph in VE? So we have three ways we learn to get a transitive closure. Who remembers what they are? You can write them. So who was just asking? A binary search tree, don't know about B. Okay, so we can use DFS. Yeah, we'll come back to the DFS in a moment. So what are the other ways we get a transitive closure? So with the standard ways using Warshaw's algorithm, right? Warshaw's algorithm is specifically made for the transitive closure. Another way we talked about is to do matrix exponentiation. So you take a to the 0, a to the 1, a to the 2, a to the 3, up to a to the n minus 1, and you do the Boolean sum of those, and that, well, if it's true, if any of them are true, that means there's a path. But the third option is the one that's being asked for over here, which is the transitive closure by doing DFS. So as Daniel said, you do DFS for each vertex, right? And you look at all the vertices that are reachable from that vertex, right? So if I run DFS from vertex 1, and I see what vertices could I reach in the DFS, so that's going to be my row, right? All of those are going to have a 1 in them. Then I do DFS again from vertex 2, and I see what vertices are reachable. I have to reset all the visited. How do you determine that we need DFS? So that's a good question, right? So again, we have three algorithms, but we also have to look at the time complexity, right? The time complexity for Floyd is V cubed. The time complexity for the matrix multiplication is more like, a V to the 4th. So if you want to get V to the VE, you could use DFS. Question is being asked, can you do BFS? Will BFS work? Yes, you could use BFS as well. It'll have the same time complexity, but BFS will work as well. Basically, you're saying what vertices are reachable from the vertex. Yeah, so again, you're doing BFS V times or DFS V times. All right, next question is about the topological sort. So first of all, we have to remember what a topological sort is. It's a way of taking a graph and flattening it. Okay, what do we mean by that? It's saying if I have to order them in a flat way, right, what way do I do them so that I don't violate any precedence relationships? So basically, you output them in reverse finish time order. Now, keep in mind that the things near the top of the graph, right, closer to the source, are going to have a higher finish time because you start with them, but you don't finish them until you did everything beneath them. So you do a DFS, get the start and finish times, the begin and end times for each vertex using the enhanced DFS, and then you output them in reverse finish time order, and that will be the topological sort. Okay, determine in V plus E time the strongly connected components of a directed graph. I don't think we did that, but how could you do that? Well, again, you could use DFS for a vertex. So what does that tell you? It tells you all the vertices that are reachable from a given vertex, and then you would need to run it in reverse direction, right? So we can do it in both directions, because strongly connected means what? Means both directions, right? I can go from A to B and I can go from B to A, or not just A to B and B to A, but everything in the component, right? So that would work. But that one, I don't think we talked about strongly connected components. All right. Determine OV plus E time a mother vertex of a directed graph. Okay, so I get we didn't do that either, but that is a vertex that from which you can reach all the other vertices if there is one. So again, these tend to be DFS based. Okay, when you see V plus E, that usually means some kind of DFS. Right, determine OV time if directed graph is a star. Right, how do you tell if something is a star? So I don't, I'm just thinking if you can you do this in V time? I don't know if you can do this in VTime. Right, once you know which is the center vertex, then the good news is you don't need to, oh, okay, yeah, you can do this in VTime, right? Because you go through the vertices, all right? You go through the vertices. Now, if it is a star, this is an interesting question. If it is a star, right, what is going to be the number of edges for all the others if it's a directed graph? So one vertex will be adjacent to everyone. So basically what you do is you go through the adjacency table, right? For each vertex, what do you expect to find for most of the vertices? I think you're writing something there. For most vertices, what will you find in their adjacency list, in their linked list? Nothing. Right? Cheng says a single item, right? Just the vertex itself. So basically you go through the adjacency table. For each item in the adjacency table, you will have nothing. You'll have like a null pointer, right? So that takes one operation. And when you hit the one that is the center, you go through it and make sure it has v minus 1 neighbors. Okay, so that's sort of a cool question. It actually is easier to do in the directed graph than in the undirected one. Okay, determine O of E time whether an undirected graph is bipartite. Okay, what's the basic strategy to determining if a graph is bipartite? Basically, you color them, right? So you do some kind of search on the graph and you color them. And if the thing is colored already, the opposite color of what you need to do, then it's not bipartite, right? So remember, you're alternating, right? So if you come from a red, you color the next one blue. If you come from a blue, you color the other one red. So what are you really doing here? You're going through all the edges. Okay, you need to hit every edge. So that's why it's going to be O of E time. And determine whether an undirected graph is complete. Okay, how do we know if an undirected graph is complete?
Each vertex is connected to other vertices.
Is connected to every other vertex, right? So how do you do that? Basically, you go through either the row of the matrix or the linked list. So that's going to be V squared. But what is E in a complete graph? How big is E in a complete graph?
V minus 1.
Well, it's V times V minus 1, which is basically V squared, right? So what we're really saying here, there's a little bit of a trick, right? It's saying this is V plus V squared, because we know how many edges there are. It's going to be order of V squared, V times V minus 1 divided by 2. So the time complexity is going to be O of V squared, okay, which is E, all right? Do you like that question? Okay, let's go through this, because there is a question like this. Okay, well, we'll take that in a second. So let's just make sure we can recognize these. Anyone recognize this one? That's matrix chain multiplication, right? We're saying what is the cost of the chain from I to K, the cost of the chain from K plus 1 to J, and then the cost of multiplying the result of that chain with the other chain. All right, this one here, anyone recognize that?
Bellman-Ford.
Bellman-Ford. Bellman-Ford is one that checks for negative weight cycles. It can handle negative weight edges. Dijkstra can't even handle negative weight edges, right? This one here.
Fractional knapsack.
That's the fractional knapsack problem. Good. All right, this one here. So we're obviously visiting all the vertices, so that narrows it down to probably either DFS or BFS. Which one is this?
BFS.
It's BFS, right? Because we put all the neighbors on a queue and then we go back and visit them again, right? What about this next one here?
Floyd.
Yeah, that is Floyd, right? Notice again, the intermediate vertex is on the outside, as opposed to, let's say, single source shortest path turned into all pair shortest path, where the source vertex will be on the outside. All right, what about this one here? We didn't spend a lot of time on that one, but we did do it, and it's pretty easy to identify. There's
Is
nothing
it
else
the
looks like.
maximum flow?
That is the maximum flow, the Ford-Fulkerson method for maximum flow, right? Okay, this one here. This looks like the, is this the biggest triangle or the smaller triangle? This looks like some kind of a minimum triangulation problem. We didn't do that, so don't worry about that guy there. Well, what about this? In my 220 class, we actually coded Kruskal and Prim together. That was fun. That was a fun exercise, actually. So that's a hint. Okay, I think it's the only one in this semester that had anything like this. We had union, right? We did union find.
Kruskal.
Right, so in Kruskal's algorithm, we find the two components and we see if there are different components, then we need to add the number of edges, and this edge gets added to the minimum spanning tree. So result is the edges in the minimum spanning tree, and we do a union of them. And what do we have down here? Anyone recognize this one? That's also fractional. That's also a knapsack problem, but which kind of knapsack problem is that? That is the 0-1 knapsack problem with integer weights. So that enabled us to do a dynamic programming approach. And finally, what is this last one here?
Fibonacci.
That is Fibonacci doing it sequentially. Okay, how do I know it's integer weight? Well, I remember the algorithm, but it's got to be integer weight because I'm subtracting off the weight minus 1, right? So that only makes sense if it's incremental, right? Otherwise, subtracting 1 if the weight is the capacity is, the weight is capacity is 2.7, subtracting 1 doesn't mean anything. Okay. So what was the question? Someone asked a question before. They had something they wanted us to look at. Summer 2018. Okay. Do you have a page number? That was helpful, actually, having the page number. $37. Okay, this one here? Yeah? Okay, so let's see what we have here. For each of the following, identify the algorithm from a course associated with the name indicated, describe the approach and state the algorithm's time complexity. All right, so what does Dijkstra solve? SSSP, good. Describe the approach. So it's a greedy approach. Is that what we want? We want the. I guess we'll call it greedy, right? We're not going to describe the whole algorithm. It's a greedy approach. What's its time complexity? Well, that really depends on your implementation. So we talked about 3 implementations. One of them was O of V squared. That's the adjacency matrix plus the some kind of array for storing the keys. We had using an adjacency table and using a regular heap to store the keys. So that got us down to O of E log V, or O of V log V plus O of E log V, but E log V is dominant. And adjacency table plus a Fibonacci heap got us down to V log V plus E1, which is either V log V or E, probably E. Okay, describe an alternative. So what's another way to get the the single source shortest path?
Bellman-Ford.
Bellman-Ford, that's right. And its time complexity is O of V times E. Next up, problem solved, Floyd. I'm sorry, name is Floyd. What problem does it solve?
All paths shortest path.
All pairs shortest path, good. The approach is a dynamic programming approach. Time complexity is V cubed. And what's another way to solve all pairs shortest path? And we just discussed it a few minutes ago, right? Use Dijkstra or Bellman-Ford, run it for each vertex, and that'll be V times whatever we discussed a minute ago. All right, next up, Kadane's algorithm. So Kadane's algorithm finds a maximum sum subarray, right? Basically looks at contiguous elements in an array, says what's the largest sum we can get. This approach is a dynamic programming approach. Time complexity is linear. And what's an alternative to that? The B word. It finds the sum, and it also, I think, keeps track of the position. I think it does keep track of where the position would be as well. Actually, I think the way we implemented it, it just found the sum, but you could also add another variable to keep track of the position. The start and the end, if you really want. Okay, so what's an alternative to Kadane? Not a very good alternative. The brute force, right? The BF, not boyfriend, BF, brute force. Okay, and what does it do? And not best friend either. Brute force is generally not your best friend, but it's a fallback friend. You know, they're the friends you don't really hang out with so much because they're not so cool. But then when you need someone to cry your shoulders on, they're there for you. So the brute force does that. It's the fallback approach when you can't come up with anything better. All right. So Karatsuba force is you use brute force, and the time complexity for that. Well, you look, if you really use brute force, it's all pairs, and then you find the sum. So that could be as bad as n cubed if you're really sloppy about it. Right? Prim's algorithm. What does Prim do?
Minimum spanning tree.
Minimum spanning tree, and describe its approach. What design technique does it use? Greedy algorithm. It's a greedy algorithm. All right, what's its time complexity? Well, it's sort of like what happened with Dijkstra. So we have V squared if we use an adjacency matrix and a regular array to store the keys. It is a V times log V plus E times log V if we use an adjacency list and a binary heap. And it could be V log V plus E if we use a adjacency table and a Fibonacci heap. What's an alternative to Prim?
Kruskal.
Roscoe's minimum spanning tree algorithm, and its time complexity, well, it depends on your implementation, but if you use the compressing find and the union by rank or weighted union, then you can get it down to basically linear, and so it's dominated by the sort. So it could be E log E for sorting the edges. By the way, if you ever go to Geeks for Geeks, they have, listen to what they did. They have a few versions of Kruskal, but one of the versions of Kruskal that we found was for an adjacency matrix. You know how they don't sort the edges. Every single time they need an edge, they go through all v squared edges in the adjacency matrix, all v squared possible edges, and they keep track of the minimum. And they also keep track of, have you visited, that edge before? Really bad. Okay, Strawson.
Matrix multiplication.
Matrix multiplication. And what strategy does that use? Strategy is a divide and conquer. Divide and conquer. And what's its time complexity? Order of n to the log 2 of 7. So somewhere between n squared and n cubed, approximately n to the 2.8. What's an alternative there? Either, standard matrix multiplication in n cubed time, or the simple divide and conquer, which is also an n cubed time. Okay, Warshall's algorithm. Correct. Transitive closure. And what other ways we have for transitive closure? So we talked about that before. We could, a few things we could do. We could do DFS from every vertex. We could do matrix exponentiation followed by Boolean sum. Those are two more. A third one would be to use Floyd and then just check if the shortest path is less than infinity. So that's a fourth way to do it, right? Which is basically what Warshall's doing in the first place. Okay, did you want us to do, what was the other one you wanted us to do here? Section B, okay. So this is a review of sorting. All right, so let's sort of go in order here. So what's the first sort we usually talk about? I don't think we did it back in summer of 2018. I don't think I knew about it. It was, again, so bad that I never paid attention to it. So BOGO sort, right? So BOGO sort finds random permutations, checks if the permutation is sorted. Time complexity is, well, it's unbounded, really. We think we'll do it in like n factorial over 2, because we have to check roughly half of the permutations, but even that isn't guaranteed. All right, next up, we usually do a bubble sort, right? Bubble sort, we swap adjacent elements, make a pass through, swap adjacent elements that are out of order, do that again. Each time the largest element will end up at the end. Time complexity is n squared. Then we usually have selection sort. Selection sort will find the minimum or the maximum, either way, depending on how you implement it. Element in the part that you haven't done yet, we swap that with the current element. And that also is n squared. Then we have insertion sort, which takes, has the first part sorted, second part not sorted, and it takes the first element in the sorted part, in the unsorted part, and finds its proper position in the sorted portion, right? So each time the sorted portion will get one bigger. It'll have one more space than before. We also talked about a stooge sort, which is a divide and conquer, but a bad divide and conquer. So it sorts the first 2/3 of the array, it sorts the last 2/3 of the array, and then it goes back and sorts the first 2/3, right? We had the cocktail sort. What does a cocktail sort do? Which other sort is it similar to?
It sorts the elements from both sides.
Yeah, it goes forward
Kind of
and
like
backwards.
a variation of bubble sort.
It's a variation of bubble sort, correct. All right, very good. So we go, left to right, and we get the, the largest to the right, and then we go to the left, and we move the smallest one there. Back and forth, back and forth. Okay, so that was cocktail sort. We also had shell sort. Shell sort is sort of like an insertion sort, and instead of, always looking at the next element over, it does it in gaps, and the gaps gradually decrease. It's supposed to be, somewhere in between n and linear and quadratic. So the estimates are like n to the 1.5, different numbers like that. We found it actually performed pretty poorly. That was what I saw from most of the students, that shell sort in practice didn't do so well. All right, then we moved on to the linear-rhythmic sorts. So we have a merge sort, divide the array in half, sort each half and then merge the two results, n log n. We had heap sort, where we maintain a heap property. Let's say the largest is on the top, we move the largest to the end, and we restore the property, and then we do that again. It's also n log n, even in the worst case. We had quick sort, where we, somehow get a pivot. We make all the elements less than the pivot on the left, all the ones greater than the pivot on the right, and we recursively sort each part. Quick sort is n log n in the average case, but O of n squared in the worst case. Those were 3 n log n sorts. Then we moved on to some sorts that use non-comparison based sorts. So we had a counting sort. We basically keep track of how many we have of each thing. Then we output them. So if we have 4 zeros, we output 4 zeros, and then 3 ones, and no 2s, and then 5 4s. So we just output the right count of each thing. All right, we had a radix sort, where we use a counting sort digit by digit. Generally, it's done starting from the least significant digit, rightmost digit, but there is a version that goes the other direction. Then we have the bucket sort, where we group the data into buckets based on, let's say, where they would stand in a range, and then we sort each bucket. The trick is keep the bucket small, and then we can use something like an insertion sort. So I think that was pretty much it on the sorting. All right, other questions? This is fun. As I go through these exams, I like to think back to where I taught that course, which room we were in, which students were in the class. I think about actually teaching in a classroom, writing on the board, no slides. 2018 was a long time ago. Page 40. Okay. Consider the problem of searching for an element key in an array of integers. Describe at least 5 distinct approaches to a solution, including any assumptions about the form of the data, and use asymptotic notation to state the average case time complexity. Okay. Oh, he wants number 7. All right, let's look at number 7. Okay. This one here? Daniel? Yeah? Okay. So describe how exam sort works. All right. Ilma, what sort is this?
Cocktail sort?
This is a cocktail sort, right? How did you know that? Well, because I called on you and you identified it before. Okay, you're going in both directions. Everyone see that, right? So in this loop over here, we're going from start to near the end. We swap if necessary. And I'm going to come back to that in a second. And then here we go in the other direction. We go in the other direction, okay? What is the significance of this Boolean variable here? This is a Boolean variable, and we have this Boolean variable here. What's the significance of that?
It means that a swap has happened.
It means that a swap took place. And actually, this is, we really should do this swapped differently. What? There's a little bit of a bug here, I would say. We should say swapped equals swap or swap if necessary, right? Yeah? Everyone get that? So it depends on how swap if necessary is implemented, but I would say this. I would say swapped equals swapped or swap if necessary. I can't see my chat box. If necessary, is it I? Yeah. Okay, everyone see why it's good to do that? Because we want to know if there are any swaps over the loop, not just if the last one was swapped. Okay, so Ilma, you were saying why is that important?
Because a swap has taken place, that's why.
Well,
You're
it
setting,
means a swap has taken place and therefore what? So the hint is, you see where it says add code here? You want
yeah,
to see where it says add code here? What code would you write there that would take advantage of swapped?
we can finish early if
You can
no
finish
swap
early.
has taken place.
So you could say if not swapped, return. Yeah, because that means there's nothing out of order anymore. So we're done. You could take advantage of that. All right. Did that answer all the questions? So we described how exam sort works. It's also known as cocktail sort. In what ways it's similar to another algorithm studied in class? That was the bubble sort, except it's in both directions. In what ways it's different? Well, again, it goes in both directions, not just in one direction. How does exam sort aim to improve over the algorithm mentioned in C and D? Okay, well, C and D are different, right? So it is the cocktail sort. The advantage here is that we're exiting early. So I'm guessing in the cocktail sort that we did in that semester, we didn't exit early. Okay, what code should be added where it says add code here? So again, as Ilma said, we can exit, right? Implement the method swap if necessary. So basically you're just doing a swap, right? You're swapping the numbers. In Python, that's a one-liner. In most languages, we do that in 3 lines, right? We set a temp equals A of J, A of J equals A of K equals temp, something like that. Okay, define inversion. Everyone know what inversion is? When you have a pair of elements, that the first one should be before smaller than the second one, but the first one is actually larger, right? So they're out of order. All right, let's go back to problem 6. So what are some approaches to searching?
Linear, binary, jump.
Okay, so linear, and the question asked to make any assumptions about the data. So in linear search, we don't really have assumptions, right? They should all be some kind of data type, but we don't care about the order. Binary search, right, where we divide the array in half, we look at the midpoint and we see, do we need to be on the left or right or at that position? We have a randomized binary search where we choose a position at random, not necessarily at the midpoint. Both of those are going to be log of n on average, although randomized is O of n in the worst case. Okay, but they're asking about the average. We had the interpolation search. Interpolation search was log n. We had, let's just.
Jump search.
Yeah. Do you have a time complexity for that?
Root n.
That was worst case though, right? Let's see if we get a cheat sheet here. So those are these are priority queues. We have searching here. This is a nice cheat sheet. Princeton. My son-in-law went to CS at Princeton.edu. Okay. That. Oh, this is Sedgwick. Sedgwick. Good book. Okay. All right. Okay, how does it compare to CLRS? That's a good question. Can we do that on the exam? What, you mean cheat sheet? No. Okay, how does it compare to CLRS? The answer is CLRS is much more theoretical, right? Sedgwick's books are very practical, right? He's got a lot of actual code. It's much more down to earth. The problem with at least this Sedgwick book is he doesn't cover everything. He's got like other books with a lot of the other stuff. So he broke it up over several books, and no one's going to buy several books for one algorithms course. But it's more practical. Okay, CLRS is more like pseudocode, all encompassing. but Sedgwick is more fun. It's a little more, I would say, down to earth. Okay. Again, this is fun going through these old exams. All right, other questions? So I just posted while class was in session. Let's see what this one is here. I just posted it. Here it is. Let me just change the name to adhere to the format. I change this to summer. I don't think we have this one here already. I use dashes. I use dashes. Okay. 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 Page 20. This is what, on the big PDF? Yeah. Okay. I'm going to go back to the big PDF. We'll go back to the big PDF. Okay. So you will not be asked a recurrence like this. The recurrence that you will be asked is a divide and conquer recurrence. But while we're at it, can anyone tell me a strategy you might use on this? So I'll give you a hint. The recurrence we did that was most similar to this, or at least using the same strategy, was in quicksort, right? So look at this summation here. This is going to have f of 0 through f of n minus 1. And this is going to have f of 0 through f of n minus 1. So these are going to combine to give you 4 times this thing. Everyone see that? Okay, so basically we can combine these two summations into one. How is it 4? Because here we have 1 f of k, and here we have 3 f of k's. Okay, you just have to, figure out the indexes, but then they combine. All right, but anyway, don't worry about that, because that's not, I'm telling you the recurrence is going to be, it'll be very similar to the one that we did at the beginning of today's class. Not like this. Let's see what else we have here. Given an unsorted array of integers, you want to fish a pair of integers in that array whose sum is s. Okay, this looks fun. How do we find a pair of integers whose sum is s? This is a nice thinking question, right? It's not just remembering what we learned. Okay, so let's start with brute force. Okay, so Cheng says, we'll come back to those suggestions. Cheng says iterate through all pairs, right? So how many pairs are there? There's roughly n squared, right? N choose 2 pairs. So we take each pair, we add up the sum of the integers, and if it equals to s, then great, we return that pair, right? So that's going to be order of n squared, more specifically cn2, right? So it'll be cn2 that we have to check all the pairs, n times n minus 1 divided by 2. I describe a transform and conquer. So someone suggested that we sort it. Who was that? Who suggested that we sort it up there? Who was that? Yeah, Daniel. Daniel says sort it. Okay, good. So if we sort it, well, it's not closest points. We want to find a sum. So it's a little more interesting than that. So let's say we go through the array. We look at a number, it's 7, and the sum needs to be 20. So what do we need to find to get a 20? Understand? We need to get the sum 20. We have a 7 in front of us. So what do we need to find to make it work? Someone write something here. Okay, 13, right? Correct. So how do we tell if there's a 13 there? And the hint is it's now sorted. We use transform and conquer. We pre-sorted it. How do we know if 13 is there? I'll give you a hint. We just did something like that before, right? We did searching. We had 5 algorithms for searching. We do a binary search, right? So for each element, we look for a binary search for its cognate, the number we need to make that pair, right? So how long is that going to take? Well, now it's going to be like n log n, because we need to do a binary search for each number. Yeah? Agree? Okay. Next one, describe a space-time trade-off hashing approach to this problem and state its time complexity. So that's an interesting way of putting it. But basically what we're saying is put the numbers into the array, and now we don't need to do into a hash table. We don't need to do a binary search. So let's say we get the number 7. We just do a hash to find out if 13 is there, right? So that could be, if we have a good hash table, we could get more like order 1 time. And we could determine order 1 time whether it's there. Of course, there could be some, chaining or probing or something like that going on, and it could take even longer. But if you have a good hash table, that should actually improve it, make it more like O of n. Suppose that instead of seeking a pair of integers in the array whose sum is s, we seek any subset of integers in the array whose sum is s. Aha. Anyone have anything to say about 2 part D? See, I like these kinds of questions, because these kinds of questions, not only do you have to think, but you have to combine concepts from different parts of the course. Right? So think about how many different lectures come into play in this little question here. But what about part D? Can we get 1 minute to think? Yeah, you can get 1 minute to think. Is that an O of 1 time algorithm thinking? Okay, so let me give you a hint, okay? I want you to look at the second italics. By subset is no, not consecutive, no. Just a subset. So think of the elements and the integers. Subset of the array is, think of it as like a set. All right, we call this the subset sum problem. And what do we know about the subset sum problem? So you should know something about the subset sum problem. It's one of the most important. What kind of problem? NP complete. Okay, so if you have a set and you want to get a subset whose sum is equal to some number that's given to you, then that is an n. That is The only way you know how to do that is in exponential time. Okay, so yeah. Let's look at what else we have here. All right, we have DFS. Okay, we talked about some of that stuff before. We have knapsack problem. Matrix multiplication. Shortest path, permanent cross. Okay, so there's a lot of stuff here. Let's talk about number 8. Okay, so first of all, what is graph coloring problem? So we want to color each vertex so that no two adjacent vertices have the same color. All right, that's the problem. Okay, provide a formulation of the related optimization problem. All right, so the optimization problem says what is the minimum number of colors that is required to color the graph, again, so that no two adjacent vertices have the same color. Anyone know anything about that? It's a famous problem. I showed you the book, right? I show you this book. Okay, so what do we know about it? Look at the title. See it?
The 4 color problem.
Oh, we have solution. Okay, people are answering it. I don't see their answers popping up here on the screen. Okay, is there multiple choice? Where did that question come from? No, there's no multiple choice. Okay, so there is a theorem which has been proven, which says that if I have 4 colors, I can color any planar graph. That's been proven. It was proven by a computer. It was an interesting question because is it considered a proof if it's proven by a computer? All right, but this problem is a little more interesting than that because it doesn't say the graph is planar. We don't know if the graph is planar. So optimization problem says how many colors do we need? What's the minimum number of colors we need? Also, maybe we only need 3. So we don't really, we're not really satisfied to know that you can do it with 4 colors, okay? All right, provide a formulation related to decision problem. So a decision problem would be a yes or no, right? Can you do it with 5 or less colors? Can you do it with 3 or less colors, right? That's a decision problem. Okay, the decision problem belongs to the class NP completes, right? What 2 requirements must the problem satisfy in order to belong to that class? So number 1, it needs to be an NP. Number 2, it needs to be NP hard. Okay, being an NP, okay, I say prove that at least one of the requirements is satisfied. So, you know, pretty much anyone's going to do the first one because the second one is going to be very hard. So the first one says, okay, if it's an NP, if someone tells me use this coloring, I can see if it works, right? I just check that if I know what color each edge is, each vertex is, I check if the edge, if they're not adjacent, right? For any 2 that are the same color, they better not be adjacent, right? So I can do that, you know, I just need to iterate through all the edges. Prove that, so that's easy, that's polynomial time. Okay, describe proof for a algorithm to solve the optimization problem. So basically, here's what you would do. You would see, can I color it with one color? Probably are not going to be able to do that if there are any edges, right? If there are any edges, you can't do it with 1 color. Then you try to do it with 2 colors. And you see, does it work with 2 colors? If 2 colors doesn't work, you try with 3 colors. You try with 4 colors. You try with 5 colors, right? So you keep adding another color until you solve the problem. Explain how backtracking could be used to reduce the search space. So what you do is you don't think of the whole, you know, the whole color assignment as one big thing, right? As soon as you hit a vertex, which you cannot color because there's a problem, you backtrack and you try to change the color that you did just before to something else and see if that works better. Okay, how could branch and bound be used? Well, branch and bound, remember, you estimate. So you try to come up with an estimate of how many colors you need, right? How can you come up with an estimate? Any suggestions for how you might estimate? So maybe you look at, I'm not saying this is a good estimate, but you can look at how many vertices are in that section or something like that. Okay, because that's going to be your upper bound. All right, suggest an approximation algorithm to approximately solve the graph coloring problem. Any ideas there? So again, if we don't insist on getting the optimal, we just keep using a color. If none of the previous ones works, right? So if we're on vertex 1 and I go to vertex 2, well, I just use another color. If I go to vertex 3, so I see if I can use any of the existing colors. Otherwise, I try something else. So I just keep trying something else. I don't do the backtracking, right? I don't do the branch and bound because that is still going to be polynomial time. So if I need a new color, then I use a new color. I don't try to fix what I did so far. What does that remind you of? Does that remind you of another algorithm that we did in this course, the strategy I just suggested? Ilma, why am I asking you? Not just because you're smart and you're the only one that keeps your video on, but what did you say? I think it was yesterday's class. It was yesterday's class. What algorithm were we talking about then? Inpacking. Next fit, right? Next fit. So this is like a next fit. It's not really fitting, but it's saying, okay, I just care about, getting the next one right. I don't try to make anything so perfect, right? I'm saying if I can't color that I want to use doesn't work, just change the color, right? I try the colors that I have, doesn't work, I use a new one. So is it like next fit? Is it like first fit? I don't know. But the point is, in this approximation algorithm, I'm not trying to go back and say, oh, you know what, maybe I could do better. So I just introduce a new color whenever I need it. And the more colors I introduce, the easier it will make other parts of the graph. Okay, what do we have left? Professor, is it possible to know our final grade before the 14th, which is the last day to drop the course if necessary? Are they still doing that, or they let you drop the course like in the middle? Today is the, yeah, I don't know. I don't know. Just do well tomorrow. Don't make this complicated. Okay. All right.
I have a question on the homework still today.
A voice. Okay, yeah.
So assignment 8's due today, and I was wondering, can we bring it in like tomorrow latest?
Yeah, tomorrow's fine.
Well, what about the Xi books? I'm almost done with it. Like
The Xi book is due Friday.
Oh, the Friday? Okay, thank you.
Okay. Again, assignment 8 is just you're adding like 2 more recurrences. So it's basically we did 18. We did the infrastructure and 18 recurrences. You just need to add 2. So it's not a big deal. But yeah, tomorrow night is fine. All right, let's see what else we have here. One approach to sorting numbers is place all numbers of approximately the same size in separate buckets, sorting each bucket and then concatenating them. All right, that's not particularly interesting. Okay. Let's do number 5. We had an assignment about that. Okay, using asymptotic notation, state how many multiplication operations are required to multiply an m by n matrix by an n by p matrix. What do we have to say about that?
We have
We
n
could
times-
do 10, but 10 is not going to be as useful to you. So I'm giving you some inside information.
we can do m times p multiplication operations.
Well, it's m times p elements times n each, right? So it's going to be m times n times p. Okay, show the recurrence equation that governs Straussen's divide and conquer. Okay. Okay, so what is that? T of n
7t.
equals 7, correct? N divided by 2, because you have 7 sub problems. Each is 7. Did we do that one in the program in assignment 8? That's a good one to do.
Yes, we did that.
We did that one? Okay. Okay, and the time we're using master theorem, we're going to get O of n to the log 2 of 7, which is like around n to the 2.8. Describe a brute force approach to the explanation of a matrix. All right, so what do? Well, we take the matrix and multiply by matrix. That takes n cubed time, assuming it's an n by n. And then we multiply that again. That takes another n by n. So if I do that, I don't want to say n, I do that p times, so it's going to be n cubed times p, right? N cubed. Yeah, and I guess multiplying it by p is the number of times, right? Is that right? P is the power. So the power will often be n, but it depends on what p is. Okay. Describe more efficient divide and conquer approach to the exponentiation of a matrix. Anyone know what to do there? Let's say we want to find a to the p power. How do we do that? So I'll give you a hint. Think about how to do a, where a is a scalar to the p power. So remember, we did a to the p over 2 and multiply that by a times a to the p over 2, but it's the same subproblem, right? So you're doing the same subproblem on the left and the right. So your time complexity is going to look like this. It looks like it's two subproblems. Okay, this is for the scalar, but it's really one subproblem. So it becomes like this. And what's the solution to that? That's T of n equals O of log n. So if I go back to the matrix one, I have T of n equals, so it's half the size plus I need to do a multiplication n cubed. So this is going to be n cubed log n. Or log p, if whatever the power is. Okay, and explain how to use explanation of a matrix to count paths in a graph. So we talked about that before, just mention it again. And that is right? So if I take a to the p, for example, right, will tell me how many paths of length p exist between I and j, right? So a to the p, and then I take ij, tells me number of paths of length p between vertices I and j. Okay, so I think that more or less wraps it up. Any other questions? So again, the structure of the exam, we have 8 problems, broken up into 2 4-problem parts, a few-minute break in between the parts. You get part 2 after you submit part 1. Come back from your break if you want to break, or you can just go straight into it. And it's best 7 of 8. So I encourage you to do all 8 problems, and I will take the best 7 of those. Okay. In college. What was that referring to, Alan? The exam is in the college. Yes, it's in person. I will actually see you for real, not just, pixelated. Room C205. See you in C205. Why don't we end like that? Oh, what is the top? So I will tell you this, hopes and dreams of online exams are finally over. So one of my students in 355, where we did have an online remote exam, told me that he has COVID, and my exam was worse than COVID. And he told me the day before how sick he was with the COVID. So I'm not sure if he has the same ideas, hopes and dreams that Daniel does, but at least not after seeing my online exam. See, with online exams, professors have to work very hard to ensure, or at least try to preserve integrity. And sometimes we have to we work too hard. So, yeah. Okay. What was the top hat code for today? 6693. All right, take care, everybody.
Thank you,
See
Professor, for this
you
amazing
all
answer.
tomorrow. See
Thank
you
you.
tomorrow. All right, I think we need a round of applause for Ilma for holding the fort. All right,
Thank you.
bye-bye.
Professor, quick question.
Yes,
When will the recording be up for today's class?
when will the recording be up? So it usually like an hour after my next class, so around 3 o'clock, I would say, because it's got to record, it converts. I don't even know exactly what it does.
Okay,
So it'll be around 3 o'clock. Okay,
thank you.
okay, bye-bye.